Fortunate for us, we can look at the monarch butterflies, we can look at the sea turtles, we can look at the whales, put that all together and build the best system and be able to navigate anywhere in the world.
In terms of the animal kingdom, they have figured it out. For us now it's to understand how to decipher how they do that so that we can put it back into our robot.
When I saw this ship standing there and a plane going over the top and a couple of guys, you know, peering over the top of the upturned hull, it was a miracle.
There certainly are some parallels with the animal kingdom. A lot of our people who are writing the software for these aircraft have based some of their initial algorithms or software code on things that happen in the animal world. Animals are very big on cooperating, such as bees in telling each other where the hives are, ants in telling each other where the source of food are, geese in terms of navigating where they're going to fly. It's this sort of synergism that we're hoping to utilise in the aircraft. Not the actual aircraft themselves that are special, but it's the things on board, what we call the payload. So it's the computers, and in particular the software or the algorithms they run and what they can do.
Okay, that's good.
In this particular case is that we're trying to avoid using GPS for navigation of the aircraft. GPS, or Global Positioning System, is not going to be available all the time in all the applications that we're looking at. Underwater and underground, GPS is never available. In a military application, GPS may be turned off or it may be jammed. So what we're trying to do is to work out how to navigate without using GPS.
Okay, Dave, you're clear for takeoff.
way the technology works is very similar to the way that you navigate if you walk into an unfamiliar building or a room. You walk through the door and you take note of the fact that you've got the edge of the door, which might be a prominent feature in that room. There might be a window, a piece of furniture, and you move around the room and you note subconsciously your position relative to those features in the room, and the computers on board the aircraft are doing a very similar thing.
Airspeed 75, altitude 445.
They're looking at dominant features on the ground. They note the position of the feature. As they move past the feature, they note the position of other features. They build up the location of those features on a map which is stored on the computer. And when they return to the same area, they look at the feature again, and by looking at its relative position, they're able to determine the position of the aircraft.
Okay, taking off now. Stu, ready for autonomous?
Enabling autonomous mode.
Going autonomous.
Altitude 450. Airspeed 70. Altitude 412. Airspeed altitude 430.
Flight duration 60 minutes.
The laser on the aircraft is used to tell the camera system how far away it is from the targets. With an ordinary camera, it tells you the angle to the target, but it doesn't tell you the distance. If we have both the angle and the distance information, then we can determine the position of the target on the ground.
How's the height and speed?
Altitude 470.
It's able to share the information gained from those sensors with other aircraft and build up a complete map. The objective of the next phase of this project is to be able to send an aircraft out on a mission so that it's able to build its own map and perform its mission objective and then return without using any GPS information. And we're also developing technologies so that that map can then be shared with other aircraft, and other aircraft can also navigate using the same map. There are a number of applications for this technology, and a lot of them are not in an aerospace environment, but actually in a land environment. One example is search and rescue, where robots are required to enter collapsed buildings or tunnels and search for people. Another application is where a miniature aircraft, not much larger than your hand, will be able to fly into buildings and build up maps and go into areas that are hostile to human beings.
In terms of the animal kingdom, they have figured it out. For us now it's to understand how to decipher how they do that so that we can put it back into our robots. Mother Nature has the answer. It's just to us to get those answers and translate them into technology. Hyperion is what we call a test bed. It's basically a robot, a platform that we will use to test new navigation, new ways of going around obstacles or new ways of doing science. Robots are, for the time being, surrogate geologists that we send on another planet. So we are trying to have them do as much as we would be doing if we were going to Mars. Time has been doing on Mars what it did on Earth. Bring layer upon layer upon layer of different materials, and this has deposited sediments and rocks. This is this diversity that we need to explore if we want to understand Mars and its environment. And this is also why we need to learn how to navigate with robots so that we can go from one target to the other and also achieve long ranges, long distances, because you won't understand the global history of Mars by staying in one place. To be able to drive on Mars, you have to have a very smart robot. You need to have a robot which understands what's in front of him, capable of avoiding obstacles, because you cannot communicate very often with the Earth. So your robot needs to understand how to go from point A to point B without avoiding being in trouble. So this is a very smart piece of equipment. In 2003, we took Hyperion to the Atacama Desert, which is basically the driest place on Earth, and very similar in many respects to Mars. So it's important to bring a platform like Hyperion there. And our goal with Hyperion in the Atacama is to do what we call now robotic astrobiology. One of the achievements of Hyperion was to demonstrate a 6-kilometer traverse using synchronous navigation. So it's really the new generation of robot. You have beautiful landscapes that remind us very much of the Earth. Ancient rivers, valleys, dune fields, polar caps, volcanoes. Everything is there on Mars that we know on Earth, except maybe for the scale it's often much bigger than on Earth, which is really interesting because Mars is about half the size of the Earth. Long-range rovers will come. We will start with several kilometers, but in order to understand the planet, we'll have to go hundreds of kilometers. And if we are lucky, maybe we'll find these traces of life over there. I really hope so.
What's so unique about it is that we are using a force other than the muscle power of the surgeon to manipulate instruments inside the body. In this case, we're using externally applied magnetic fields that are very precisely controlled. This particular one is in the left temporal lobe, which is in a very critical location because it's the left temporal lobe that controls a lot of the speech functions that allow a person to interpret words, read, and formulate speech. What we think the magnetic stereotaxis device is going to allow us to do is to guide very precisely a magnetic catheter all the way along this route and deliver glue or other embolization materials to the center of the malformation, blocking these little blood vessels off. When we did it on the first patient, we sort of had this moment where we said, God, this thing really works. And it was very exciting as we were watching the catheter track to its target. We really think that we've made a lot of progress with this device, and it's very exciting.
whenever the bacterium responds to TNT, it thinks it's turning on the genes that will eat that substance as a meal. Instead, it's turning on the genes that we're interested in and becomes fluorescent.
And this is the negative control for it. It hasn't been sprayed. Got it, it's right there.
Most likely we have a stacked array of mines here. And what that means is the detonator would be removed from the top mine where we have no metallic signature. And then we have mines underneath that are armed. So if you apply pressure, you'll get click, click, and then the one underneath will detonate and all three of them will go.
The current mine clearance methods, it's a very slow, laborious process. And what's more, you can look at huge tracts of land that have no mines on them at all, and which people still have to cover in that very laborious fashion. With the method that we've developed, we have the opportunity to examine those very, very quickly and tell whether, yes, there are some mines there, this area should be looked at, or no, there are no mines here at all. For instance, if you wanted to just do a road, you could go down the side of the road that you knew was free from mines and spray it with a hand sprayer. For the future, what we'd like to do is load this onto crop dusters and crop dust a field with the bacteria.
Out here at the test bed, we're using the tractor with the sprayer rig. We could use a sprayer rig in a real field operation where we would have it mounted to one of our armored vehicles with steel wheels that goes into an area and then look for detection that way. But it's ideally suited for an aerial platform such as a helicopter or a light airplane. As an end user in the field and someone who has been in the minefields and worked in the minefields, I see the microbe as being one of the most important technologies to come along for detection of landmines in the field.
When you think about the magnitude of this problem, perhaps 100 million landmines still out there, 100 million people that could be killed, maimed, including the children. It's heartbreaking to see that when you see the photos like that in the newspapers. Being able to overcome that problem would just be a phenomenal thing to do.
Newer mines can actually be triggered by sensing that a ship is in the vicinity. So they may listen for the acoustic signal, the sound signal coming from a ship, or they may respond to the magnetic field of a ship, or they may respond to the pressure wave. Instead of just having one beam directly below the boat, you have a whole splash of sound across from left to right, and you can get the depth of water across that swath, as we call it. And as the boat travels along, you build up a whole picture of the depth of the seabed. If we know what the seabed consists of, then we can plan strategies for protection against mines if there were a mine threat. Another area is for safety of navigation. It's very important to know how deep the water is.
It's not a threat to shipping or anything like that. It's well out of the way.
Dive. Dive.
Feet, sir. 6.
Just keep an eye on those biologics there on the left.
The biologic sounds can get so loud out there, especially when whales or dolphins are mating. The sound is so loud, the sonar supervisor, he'll have to take his headphones off and just listen to the screeches and yelps of the animals that are out there.
Well, 90 feet, sir.
Passive sonar is just listening, where active sonar you have to send out a pulse or some form of energy into the water and then receive back that piece of energy. For a submarine, it's important to use active sonar to determine where the bottom is. We use a fathometer send a pulse down to the bottom. That signal comes back. We read that based on what we know of the charts. We can tell where the ship is if we get a number of pulses, put all that information together, and we can get, like we get a global positioning fix, we can get a bottom contour fix. It's important for submarines to stay stealthy. In order to stay stealthy, completely stealth and undetected, we don't want to be breaking the surface. There are things out there that can detect our antennas, but there's nothing out there that can detect us as long as we stay submerged.
Dive submerged ship, make your depth 160 feet.
The latest innovation in navigation for submarines is the use of the gravity field of the Earth. Lockheed Martin has developed a system that uses the Earth's gravitational field to navigate and be able to estimate the terrain, the surrounding terrain of the vehicle. The force of gravity changes as you go about the globe. If we had a perfectly smooth, homogeneous sphere, the gravity, the direction of gravity would be normal to the surface of the Earth or perpendicular to the surface of the Earth, and it would be constant as we traveled around the surface of the Earth. But unfortunately, that's not the case. We have topographical variations due to hills, mountains, valleys, oceans, rivers, plateaus, and other types of variations. And that actually distorts the gravity vector. We actually use that signature to navigate. If you were to pull apart this instrument, what you'd see inside is 4 accelerometers mounted on a common base, rotating at a constant frequency. The output of the accelerometers are combined together, and signal processing is applied to allow for the gravity measurements. The reason the three-dimensional image is important is because what it does is it gives them an image of the surrounding terrain, much like when you're playing a video game and you see the action and you see the terrain or the building that you're in. And right now, submariners do not have that ability to see. There's 2 main functions that the gravity module employs. That's terrain estimation and passive navigation. It accomplishes these 2 functions without emanating any signals. So therefore, it's totally covert and it's very, very accurate. With this type of system, we'll be able to navigate in littoral waters. We'll be able to navigate in enemy harbors and up enemy rivers and essentially have the edge on the enemy. The gravity module has lots of different applications. Not only is it good for navigation, passive covert navigation, it's also an excellent surveyor for minerals and hydrocarbons. Both shipborne and airborne systems have been deployed to date.
The reason for making these maps is not just to provide future astronauts with a way of finding their way about the galaxies. Because with the technology that we have today, we don't believe we will ever be able to travel between galaxies. The distances between them are too great. They're measured in hundreds of millions of light years. However, if we can plot the positions of galaxies in large enough numbers in a three-dimensional space, then we can begin to see how they're spread around in the universe, how they're distributed. There are areas where galaxies clump together in large numbers, which we refer to as clusters, but there are also voids between those clusters. And when you look at these things on the largest possible scales, that's to say on scales of more than about 300 million light years, you start to see that the way galaxies are distributed through the universe is not just clumps and voids, it's actually almost a honeycomb structure. And the galaxies populate the edges of these honeycomb cells. That actually sheds light on the mechanisms that caused the universe to evolve to the shape that we see it today, and in fact sheds light on the Big Bang itself, the event in which the universe was created about 13.5 billion years ago. We allow an electronic robot to pick up the fibers, move them to the right place and put them down with an accuracy actually of better than 1/100th of a millimeter. So it's much better than doing this by hand. So the robot essentially aligns the fibers with the target galaxies in the sky. So you ignore all the other information and just select the information from those objects. Then you take the plate out of the robot, load it in the telescope, point the telescope at the correct piece of sky so that the fibers themselves align with the target galaxies. And lo and behold, the light from the galaxies comes down the fibers and we can then analyze it and look for these spectral signatures. You're like a navigator because you are revealing new things. You're making discoveries about the universe that were unknown before in exactly the same way as an explorer would make discoveries about the Earth in a sense that was unknown before. You get a feeling of elation because your horizons have been broadened, you've seen new things and new worlds in a sense.